Hello and welcome to our channel, and today we are going to discuss about CMOS inverter. We have already designed it in Virtuoso and then we designed it in Incisive as well. Okay, so that means we have covered this both in analog and digital. And I'm sure if you are learning VLSI, that means you are in either 5th sem or 6th sem, and that means that you have already completed the subject digital electronics. You've already completed digital electronics and you are well accustomed with the symbol of our inverter. And what was that we were giving? Input was A, output was Y, and the truth table was, if I am giving a logic 1, I am getting logic 0. If I am giving logic 0, I am getting logic 1. Basically, it was inverting whatever input we are giving, right? And in both Virtuoso and Incisive, we have proved that we are getting this as our output, right? And this is the schematic. This is the schematic in our Virtuoso lab that we have completed, isn't it? So we are well accustomed with this diagram. Now, we know that the logic of an inverter is whatever is the input, output will be its inversion. That means if I am giving a logic 1 here, I am getting a logic 0 as the output. If I am providing the input as logic 0, then the output will be logic 1. And this is the circuit. And we know that from our analog lab, that is the Virtuoso, okay, it is Virtuoso, that this is the NMOS at the bottom, and this is our PMOS. PMOS is at the top, okay, and together we know that the name is CMOS inverter. Okay, together we know that the name is CMOS inverter. So, but have you ever wondered during our Virtuoso lab that, okay, this is the circuit, understood, accepted, but how is it converting the logic 1 to logic 0 and logic 0 to logic 1? And why NMOS is at the bottom and PMOS is at the top? It might have come across your mind while doing the lab. So let us uncover this. Okay. So today's class will be focused on CMOS inverter. Okay. But if you are an electronics engineer, you are very sure of this, that if a circuit is working for us, okay, that means there will be some predecessors of CMOS inverter. Means there will be some circuits that came before our CMOS inverter but were not giving us that desired output that we needed. Okay, so what are they? Let us see. So the first circuit was the NMOS inverter. Okay, the first circuit was our NMOS inverter, and there are two types of it. The first type was resistive load NMOS inverter. Resistive load NMOS inverter, and the circuit looks like this, wherein we can see an NMOS at the bottom. This is our NMOS, because our PMOS symbol has a bubble at the gate terminal, and in NMOS we have no such bubble there. Okay, so that is how we differentiate between a PMOS and an NMOS while covering the circuit diagram. Okay, so I can see an NMOS at the bottom and I can also see a resistor at the top. So what do we have? What is the name? Resistive load NMOS. Resistive load NMOS. That means that this resistor is our load. If it is a load, then what is this NMOS called as? What will be the NMOS called as over here? The NMOS will be called as the driver of this circuit. So we got a resistor as the load of our circuit and NMOS as the driver of our circuit, and we are connecting the load with the VDD and the driver with the ground. Okay, we are connecting load with the VDD and the driver, since it is an NMOS. Okay, since the driver is NMOS, we are connecting it with the ground terminal. Alright, and we are providing input to our driver, and from both the ends of this clubbed terminal, from our load and driver, we are getting the output. Okay, now this used to act as our inverter. And we were getting the desired output. That means we were giving a 1 over here as the logic, output was 0. If we are providing 0 as the input, then we were getting the logic 1 as our output. Okay, we were getting the output. But what happened that we left this circuit? I mean, it's just one resistor at the top, isn't it? It is just one resistor at the top. Why did we leave this circuit? We left this circuit because when we are talking about loads such as resistors, capacitors or inductors, when we try to integrate them in our IC, it is taking up lot of area. It is taking up lots of area. And what is the first and foremost thing of VLSI? That we need to scale down our design. We need to scale it down so that we can fit in more and more number of designs within the given area. So if I place a resistor in my design, it is going to take a lot of area. If it is taking lot of area, the first and foremost rule of VLSI is broken. So we can't stick with this. Okay, so we can't stick with the resistive load NMOS inverter. So we moved along. But we were still experimenting with the NMOS inverter concept. So we moved to the second design known as the depletion load NMOS inverter. And the circuit diagram looks like this. Now, here also you can see an NMOS at the bottom, but there is certain level of changes in the load. The load looks different now. So we replace the resistor with some other kind of a transistor. See, there is no bubble at the front, so it is not a PMOS. And I have shaded this area. Can you see the difference? And there is no shading over here. So this is our typical NMOS. That means we have studied this. So the driver over here is actually enhancement type NMOS. It is enhancement type NMOS as acting as the driver. What about the top one? The load is actually, instead of a resistor, we have taken depletion type NMOS. So both the load and the driver are NMOSes. Okay, but the type of NMOS is different. So at the load we have got depletion type NMOS, and it is depicted by this symbol wherein we are shading it over here. Okay, and the bottom one is our enhancement type NMOS that we have covered so far. We have taken NMOS as our example and we have covered everything, right? This is how we are describing the depletion type NMOS. More details on this type of NMOS I'll be covering up later on when our syllabus is progressing. So do not panic right now. Okay. The only thing you want to remember is that a depletion type NMOS is always on, that it is always on. And what about the enhancement type NMOS that we know? That you need to give a particular voltage to turn it on. So our driver needs a particular voltage to turn on, but the load is always on. That means, and it is also connected to VDD, power supply. That means if a certain device is always on, what is the first thing that will come to your mind? That there will be a lot of power dissipation, right? So if there is a lot of power dissipation, means it is actually not a very good design. If I am constantly losing power because of my device, that means it is not a good design. And because of this reason, we moved along from the depletion load NMOS inverter design. Mind you, the output and input were performing exactly how it should. That means if I am giving a logic 1, I am getting a logic 0. If I am giving a logic 0, I am getting a logic 1 as the output. Input and output was fine. But the reason for a good design is, over here, the problem was lot of power dissipation. And which kind of power dissipation? Basically the leakage power, which is not good. What is leakage power? That means, if, let's suppose you are studying right now with me and you are not using your phone. Let's suppose you are learning from a computer, from a laptop or tablet, okay, and you are not touching your phone. Can you assure me that your battery level will be the same after this class? No, at minimum 1% battery will be lost. Okay, so that is our leakage power. Okay, so this was the reason why we moved along from this design. Okay, now we went on to a different kind of design that is named as Pseudo NMOS inverter. Pseudo means false, NMOS is NMOS. So what is a false NMOS? PMOS. And where are we replacing it? Is the driver a cause of our problem? No, it was the load. It was the load that was acting up. We needed to improve our load part of our circuit. So we are replacing, first we replaced the resistive load by what? We replaced it by a depletion type NMOS. And then we replaced it with a PMOS. As you can see, there is a bubble at the front, that is at the gate side. But why are we calling it as false? Why not directly name it like, okay, PMOS NMOS inverter or PMOS inverter? Why not like that? Why are we saying that it is a pseudo NMOS? Because if you look at this circuit at the load side, can you see that I am grounding the gate potential? The gate terminal of my PMOS is grounded. That means I am providing a zero logic to my PMOS. I am providing a zero logic to my PMOS all the time. Okay? And I am providing the input to my driver. So what was the problem of this design then? Why did we move from this design to our CMOS inverter circuit? It looks the same, right? PMOS on the top, NMOS at the bottom, isn't it? Why did we move along from this? Because the moment we give a constant zero logic to the input of our PMOS, it will cause high power consumption. Why can I say this? How did I land up on this reasoning that if I provide a constant zero logic to my PMOS circuit, it will give me high power consumption? Because if you remember, while discussing the device structure of an NMOS, I told you to turn on an NMOS, we need a positive gate potential. Okay, and I told you for PMOS it will be vice versa. That means for a PMOS to be turned on, we have to provide a negative gate potential. What are we providing over here? We are providing a constant zero. So that is our negative gate potential. That means my PMOS is always on here. PMOS is always on. Again, if a particular device is always on, it is going to leak a lot of power. Okay, so these are the reasons why we shifted our focus, or why we landed up on this CMOS inverter circuit. Okay, now before this class started, I had released a quiz on our community. And I asked you, what is CMOS? By the way, whatever quizzes I am providing you, it is not just playful things. They are actually related to either I have already covered the logic or I am about to cover the logic. So participate in the quizzes, it will help you retain the knowledge. Okay, so the question was, what is CMOS? Now we see the term MOS and we think, okay, this is another type of MOSFET. Wrong. The answer is, it is a technology. And with this technology, what do? We create efficient ICs, integrated circuits. Okay, now we have a tendency, whenever we see a abbreviation, we tend to answer it with its full form. Okay, so whenever the question is what is VLSI or what is CMOS, say what it does, that it is a technology to create efficient ICs. Okay, and what is the full form of this? Full form is complementary. Check the spelling, it is not PLI, it is PLE. Okay, don't make that mistake. Complementary metal oxide semiconductor. Since the MOS full form is still the same, people tend to confuse it that it is another type of MOSFET. No, that is wrong thinking. It is a method in which we are using it. Okay, in which we are using it. Now let us focus on the term complementary. Let us focus on the term complementary. The spelling is COMPLEMENTARY. Complementary MOS. We have already covered MOS, so I am not going to get into it. I am only going to focus on this complementary part. Now what is this complementary and why am I telling you what is the spelling of it? See, recently February month went by, so many people are going to use the compliments to woo someone, to be in good books with that person. Okay, to attract that person. Okay, don't go into those things. Okay, just focus on your studies and career. So the complement or the complementary part over here is not compliments. Okay, That means you are not praising someone. Then what is this complement or complementary? This word means the what does come to when I am saying complementary, that means it is complementing, means let's suppose tomorrow I create a business with my friend. Okay, I have best friend forever. This is me and this is her. So together we come, we think of something and we create this business. Okay, and of course I have my list of expertise and she has a list of expertise. If both of us have the same skill set, that means she would not need me or I would not need her, isn't it? If both of us have the same skill set, do we need each other then? No. But if we have complementary skill set, that means let's suppose I can complete VLSI part, she can complete the AI part, and both of us together we created a business that is the combination of VLSI and AI, and our business is booming. That means whatever VLSI part we have to cover, I am responsible for that, I am taking care of it, and whatever AI related stuff is required, she is working on it. So I am not going to irritate her that are you working or not, why are you not working, and she's not gonna irritate me that come on, you're becoming lazy, do your work. No. And it is our understanding that okay, for this anything VLSI related, I am responsible, and anything AI related, she is responsible. So this is the complementary action. So complementary MOS means we are gonna pair up complementary. I will write CMOS only now, since now you have understood. So CMOS is a technology that pairs up a PMOS and an NMOS together to create efficient ICs. Okay, it pairs up PMOS and NMOS together to create ICs. Okay, and here I told you, right, that see over here, what did I tell you? To turn on an NMOS we give positive gate potential, to turn on a PMOS we give negative gate potential. That means whenever we are applying excuse me, whenever we are applying the CMOS technology for creating our inverter, that means when the input is zero logic, it is negative gate potential. So zero logic is provided over here and zero logic is provided over here. Tell me which one will be working? PMOS will be working and NMOS will be off. It is not going to respond to a negative potential. But if I give a positive input, that means logic 1 as our input, what will be the logic at the PMOS gate? Logic 1, of course, and at the NMOS gate, logic 1. So what will happen to the PMOS and NMOS? PMOS will be turned off and NMOS will be turned on. So like me and my friend creating a business where I am only working for the VLSI part, she is working for the AI part. That means here also our PMOS and NMOS are working on shifts. If the input is 0, that means NMOS will see, okay, 0, that means I am not required right now. PMOS you only handle, so PMOS is handling. If the input is logic 1, PMOS will see, oh, it is logic 1, I am not required to take care of this. NMOS, you do your job. So NMOS is handling the job. So because of this, it is termed CMOS inverter. Now tell me, if I am bifurcating the work, on my PMOS and NMOS, that means my power dissipation will be low. See, power will always dissipate. But our focus should be that it is low. Lower than whom? The predecessors of CMOS inverters. So power dissipation is low. What about switching speed, or by what time we will get the output? That is known as switching speed. So it will be increased, because here only I am deciding which of my circuit, either load will work or driver will work. If load is working, driver is off. If driver is working, load is off. So my switching speed, by what moment I will get the output, that will be taken care of in a speedy manner, means better than the predecessors. Okay, and we have something called as noise margins, and that is high. So having a high noise margin is good for us. Okay, don't worry, this is also going to get covered very soon, so no need to worry. So that is why we have stuck with the CMOS circuit, CMOS inverter. Now everything in VLSI will be of a CMOS design, and CMOS design, see, it will always pair up a PMOS and an NMOS. But what was the problem in our predecessors? The load. So PMOS will, PMOS is our load, NMOS is our driver. Okay, now look at this diagram, the CMOS inverter diagram. Okay, operation, we have decided that we have understood 0 means PMOS will work, 1 logic 1 means NMOS will work. Okay, now see, when I am giving 0 as our input, okay, so this 0 travels from here to both the places, load and driver, and from here we are deciding, okay, 0 is turning on my PMOS and it is turning off, means it is not going to turn on our NMOS. Okay, so PMOS is now on. Now you tell me, I have told you PMOS is on, NMOS is off, and for the logic 1, PMOS is off, NMOS is on. But what is the output? Let us see the output also, na? Whether it is going to invert or not, and how it is inverting actually. So let us start with the logic 0. So at this point, okay, let us take it. Okay, now let us only focus on logic 0. Okay, so I have provided logic 0. So my NMOS is off, PMOS is on. Alright, now look at this PMOS. It is connected to the power supply, that is VDD, and see, the body is also connected to its source. Okay, so we have got a source terminal, gate terminal, drain terminal, and this is our body terminal. Similarly, drain over here, source over here, gate over here, and body over here. So now look at this. The body terminal is also connected to its source, and both of them are connected to VDD. What is VDD? VDD means a positive potential. In virtue, so what did we give as VDD? We gave VDD as 1.8. Anything that is not 0, that means it is considered as logic 1 in VLSI. Okay, and anything that is 0 volts in VLSI, it is considered as logic 0, right? So VDD is logic 1, but the input is logic 0 over here. So what will PMOS do? Input at PMOS is logic 0, and PMOS is connected to VDD, which is logic 1. So what will PMOS do? That, okay, so logic 0 is here and logic 1 is here. So PMOS will pull it up to what level? To logic 1 level. So when PMOS is getting a 0 volt or 0 logic as its input, since it is connected to VDD, it will pull it up to a logic 1 and will pass it on as the output, and we will get 1 as the logic 1 as our output. Okay, now let us see our NMOS. Let us see the second scenario. What is the second scenario? That we are giving 1 as the logic, as the input. Now logic 1 as the input means it will travel to both the PMOS and NMOS, and PMOS will be turned off because of this input, because PMOS doesn't respond to positive gate voltage. Who will be turned on? NMOS will be turned on. So when NMOS is turned on, look at what it is connected to. NMOS's source and body both are connected to whom? Ground. Ground means what? Ground means 0 volts. 0 volts in VLSI means what? Logic 0. What is the input logic over here? Logic 1. What is the ground power rail value? 0 logic. So what will NMOS do is NMOS, and what is the input? We have got a logic 1 as the input, and it is connected to logic 0 or ground, isn't it? So we got an logic 1 over here, and it is connected to 0 logic. So what will NMOS do? It will pull it down. It will pull it down to which level? The logic 0 level. And PMOS was doing what? Was pulling it up to logic 1 level. Okay, that is why That is why the PMOS, that is the load of our circuit in CMOS design style. Okay, in CMOS design style, PMOS is called as the pull-up network and NMOS is called as the pull-down network. Okay, and because of this pulling down to the zero level, I am getting what as the output? Zero logic. So now we have successfully converted or inverted our input in our output region. So this is how a CMOS inverter works. Okay, this is how a CMOS inverter works. So while covering it both in analog and digital, we simply implemented the design. This is the actual reasoning and how the inversion actually happens. Okay, so in CMOS, the PMOS part of the design, that is the load, is called as the pull-up network, and the driver part of our design, that is made up of NMOS, is also known as the pull-down network. Okay, is also known as the pull-down network. So this part is load, this part is driver, and load is made up of PMOSs, driver is NMOS, and their different names based on what they are doing. Okay, so this is where I will wrap up our today's session. I know it is very interesting, right? And in our next class, we are going to cover the DC characteristics of our CMOS inverter. Sounds a bit too heavy, right? The concept of this. Don't worry, you have already seen this. Seen it where? In our Virtuoso lab. You remember that we had two curves. One was transient, another was DC in our radial window, isn't it? So in our next class, we are going to understand the DC curve or the DC characteristics of our CMOS inverter. I hope you loved today's session. Like, share and comment. If you have any doubts, you can comment your doubts. You can post it in our community tab. And remember, we are still on to the path of 500 subscribers. Help us reach there. Let's grow together. Until then, stay happy, stay updated. Thank you.